Hello, in this video we are going to get an introduction into parametric equations and learn a little bit of calculus that we can do around parametric equations. So first we just want to get through that definition and understand how to graph a curve, how to eliminate a parameter, and then we'll do some derivatives as well. So starting with that definition, parametric equations are great particularly for physical systems where you're kind of tracking a particle or an object through space and time. And because it allows us to add this extra parameter, which we usually call t, oftentimes it is time. And it lets me take a look at some crazy curve like this one here, and it gives me direction to that curve. And it gives me a location at a specific time t. So I can get an x and a y at a specific time or a specific t value with this. And so to make this happen, to bring in that extra parameter t, the x coordinate and the y coordinate are both going to be functions of t. So that when I pick a specific t value, I can plug it in and find the x and y coordinates for that t value. Now, usually this is on some kind of closed interval. And so the beginning of that interval would be your initial point. And then there is a direction to these. And then wherever it ends up at the end of the interval would be your terminal point. And t is our parameter here. So we have a lot of fancy words for this. It's a parametric curve. It's a parameterization. All of that is talking about the same kind of scenario that we're looking at. So let's start with how do I sketch a graph? And we'll look at how to do this on Desmos as well, because Desmos is great for graphing these. You can also do it on a calculator. I've got some videos on that if you're interested in doing it on a calculator. And then we'll see how to eliminate the parameter t from this set of parametric equations. So first with that graphing, if I'm going to graph this old school, like we initially learned how to graph things in algebra, usually back when it was just x and y's, we would pick an x value, plug it in, and get the y that goes with it. This time, because both x and y are functions of t, we're going to pick a t value, and then we plug it into both equations and get an x and a y coordinate for that t. And then I can just plot those points and I get a graph. So you end up with a table that looks something like this, where I'm picking t values and then plugging them into x and y and getting some ordered pairs. So when t is -3, I get the ordered pair 9, -27, and so on through here. And if I want to graph this, I can come over to Desmos, and I come in here, and instead of writing, x equals t squared or so on, I'm going to put parentheses in here. And then I'm not going to write x or y. I'm just going to type in what the functions are. So x was t squared. So I'm going to do t squared, comma, and then y was equal to t cubed. And then I'll close off those parentheses, and I can see it there. And it's giving me this automatic interval from 0 to 1. Let's say I wanted to do -3 to 3. Like we had on our table, and I can get a better picture of this curve. And so there's my parametric equation. So it's a little weird to get used to, but that is how you would type in the functions of a parameterized curve. Okay, so there's my little sketch of what this looks like if I were to plot those points. The other thing we can do here is eliminate the parameter, which means that I want to substitute all the t's, so I have a function that's just in terms of x and y, or at least maybe not a function, but I have an equation just in terms of x and y for this. And so really I'm just going to do a substitution. I'll say start with the equation for y and solve it for t. So t would be equal to the cube root of y. And then in the other equation for x, I'm going to replace t with the cube root of y. So it would look like this. X equals t squared becomes the cube root of y squared. And I can simplify that. So x would be equal to y to the 2/3. And I could also solve that for y if I needed to. Maybe I'm using a graphing calculator and I wanted to plug that in. Then I can just solve that for y, and then I can plug it into a graphing calculator. Your calculator does have a parametric mode, though, that you can switch to if you want to be able to type these in with the t in there as well. Okay, so let's get on to some calculus now that we're familiar with parametric equations and how the graphing works there. I can do a derivative of this, but it does get a little tricky. These formulas are here to help us, though. Just keep in mind that we're having to make adjustments to how the derivative is calculated because of that parameter t. So usually when I'm asking for a derivative of a parametric equation, that is dy dx, so the derivative of y with respect to x. So the long way of doing it would be to remove the parameter and then take the derivative, which sometimes can be rather difficult. So the way around that is to not eliminate the parameter and just simply take the derivative of y with respect to t and divide that by the derivative of x with respect to t. And what you'll get is dy dx, and you'll still have your parameter in there, which is, or you may still have the parameter in there, which is important. Second derivative gets even trickier. With this one, the second derivative is going to be the derivative of y prime, so the dy dx that we just found. And we take that derivative with respect to t and then divide it by the derivative of x with respect to t again. And that will give us the second derivative. So let's practice this, get used to these formulas a little bit. Okay, so let's say I have the parametric curve x equals e to the 2t and y equals the natural log of t. And I want to find the equation of the line tangent to the curve at the point t equals 1. So this is something that we did a lot in Calculus 1, finding tangent lines. And so we'll do it here the same way, only now it's a little more complicated finding that derivative because it's parameterized. So I'm going to start by finding the derivative. I need the slope at t equals 1 in order to find the tangent line. So I'm going to take the derivative of x with respect to t and the derivative of y with respect to t. So that's going to be 2e to the 2t and 1 over t for dy dt. And then for that first derivative, I'm going to just divide them. The y goes on top here, so it's going to be 1 over t divided by 2e to the 2t. And if I simplify that, the t ends up in the bottom. And I've got this for my derivative. Now that's just the general derivative dy dx. If I want the specific derivative at t equals 1, I'm going to plug in 1 there. And that will be my slope for this particular tangent line. So that all simplifies to 1 over 2e squared. Okay, so I found the first piece of what I need for that tangent line. I found the slope. I'm going to be plugging that into the point slope formula. And so I'm going to also need a point on that curve in order to make this work. So how about the point at t equals 1? So I'm going to plug in 1 to both of my parametric equations for x and y. So x at 1 is going to be 1 over e squared, and y at 1 will be the natural log of 1, which is 0. So I've got all the pieces now to plug into the point slope formula and get my equation. I plug in y and x and the slope, and then I'll do a little bit of simplifying by, I can drop the 0 and I can distribute the slope in there, and I end up with this equation for the tangent line at t equals 1. Now, before we leave this problem behind, let's practice finding a second derivative as well. So I can use all the information from that first one to help me out here. Remember, the second derivative is the derivative of y prime, and then dividing that by the derivative of dx, of x with respect to t. Okay, so there's the derivative of y prime, which was 1 over t. So that's going to give me negative 1 over t squared, just doing power rule there. Remember that 1 over t is t to the negative first power. Okay, and so I'm going to take that and I'm going to divide it by dx dt, which was the 2e to the 2t. And dividing those, I end up with this as my second derivative. And then to find the second derivative at t equals 1, I'll just evaluate this at t equals 1, and I end up with negative 1 over 2e squared. So that is how you find the first and second derivative and a tangent line for a parametric curve. want to do a little bit more calculus with these just to learn a little bit more what we can do. All the calculus we've been doing this semester with all the integration and applications can be done with a parametric curve as well. So arc length, for instance, is an example of something I can do with parametric. And there's just a few adjustments to the formula. Remember, before it was inside of that root was 1 plus the function squared, the derivative squared. Here it's going to be each derivative squared and then added together inside of that square root. So let's give one of these a try as well. So let's find the arc length of this parametric curve where x equals 3t plus 1 and y equals 4t plus 2. And we're on the interval from 0 to 2. So there's my limits of integration. So first thing I need is the derivative of x and y. That's the f and the g from the formula. So derivative of 3t plus 1 is just going to be 3. Derivative of 4t plus 2 is just 4. Remember, we're taking the derivative with respect to t. And then I plug those in. So square them, add them together, and then go inside the root. And then we're integrating from 0 to 2. And as well, if I simplify those, 16 plus 9 is going to be 25. And the square root of 25 is just 5. So I can integrate that, which becomes 5t. And then evaluate that from 0 to 2. So 5 times 2 is going to give me 10 minus 0. So I get a curve length of 10 here. And it might be good practice to go ahead and graph this parametric equation as well, and maybe the previous one that we did an example to as well, just so you can get a feel for what these graphs look like. Okay, so here's some more examples for you to practice on your own of each of the things that we just did together.